I cannot check per se. But the indefinite integral is always a function or a family of functions. So I can always check. The indefinite integrals, I can always check. The definite, I cannot. Just repeat the calculations in the hope that you don't make the same error twice. Now, we have what it's called the substitution rule, or it's a technique of integrating functions that are more complicated. So if I'm asked, for example, to find the integral from cosine x dx, that's a piece of cake. I know it's sine x plus a constant c, and that's done. But what if I have more complicated situations, like, and I'm starting with indefinite integrals. Something like the integral from sine applied to natural log x, everything divided by x, of course, dx. So what do I do in this case? Well, when I look at sine and I see that there is another function inside it, this, which is natural log, is a function composition, sine of a natural log, sine of another function. That's I wouldn't say complicated situation, but it's something that if I could get rid of, I would like to. Okay, so I'm going to say let y be natural log x. And you could say, okay, wait a minute. So what's with all this? Yeah, I'm using a substitution, but I can continue only if the differential of this function that I just created is in the problem. Remember, the differential is not the derivative. So when I differentiate natural log, I get 1 over x, but because I'm interested in the differential of y, I have 1 over x dx. If this quantity exists in my integral somehow, plus or minus a number, a constant, as a factor, then I'm on the right track. And I do see it. I have dx over x right here. So I can replace this piece by dy. So when I move from an integral in x to an integral in y, every x must go away. I cannot erase it. So everything, in other words, has to be accounted for. And now it is, because sine of natural log becomes sine y, and dx over x becomes dy. And this is way more human. Everything is accounted for. Sine of natural log became sine y. Dx over x became dy. So now this is very simple. It's negative cosine y plus a constant c. Because when I differentiate negative cosine, I get sine. And when I differentiate c, I get 0. However, I must go back to the original variable. So y has to be replaced now by natural log x. Negative cosine applied to natural log x plus a constant c. Now, because this is an indefinite integral, if I choose to check, I could differentiate both sides. When I differentiate here, I get this. When I differentiate the other side, I have to get the same thing. And I do. Negative cosine prime of natural log is positive sine natural log times the inner function prime, which is 1 over x. So bottom line, if I want to use the substitution in solving an integral or finding an integral, when I move from a variable to another variable that I just created, as a function, of course, I have to make sure that I have dy. There is no integral without dx, or integral without dy, or integral without dt, or anything, right? It has to have a differential of that variable. And if I'm missing a 4 or a 5 or a 10, I can easily make that up. And you'll see several examples. Okay, so this is for indefinite. I'm going to practice some more, and then I'm going to move to definite, and then I'll go back to one theorem in section 5.4. And then I'll do whatever you want me to do. Okay. So what about this? the integral from x over 1 plus x to the fourth dx. Okay, so again, I see here function in the denominator that is 1 plus x to the fourth. My starting point would be to look at this x to the fourth, and also I have in mind the fact that I know that arctangent prime is 1 over 1 plus x squared. So I kind of see something like that in there, but I'm not there yet. I'm far from it. So at this point, I will say, can I use, it's okay if you try different substitutions. It's okay. I'm just trying to explain. Could I use y, let's say, as x to the fourth? Not really, because dy will be 4x to the third dx, and I don't have x to the third. 4 is not a problem, 4 and 1/4, so that's not a problem, but I don't have x cubed. So this is not the right path. This is not the right substitution. But if I consider let y be x squared, it's a different story. dy equals 2x dx, and that's not a problem to multiply the numerator and the denominator by 2. I don't change the problem, the integral or the function, if I multiply by 2 and divide by 2. But now everything will be accounted for. This piece will be dy. The denominator will be 1 plus x squared, 1 plus y squared. Because if y is x squared, x to the fourth must be y squared. And I kind of see where I'm going. So now the new integral is 1/2 the integral from dy over 1 plus y squared. That's what I was hoping for when I saw something like that. So let's make sure now that everything is accounted for again, and then we'll finalize it in a moment. So we realize that x to the fourth, if I wanted to get rid of this, or even x to the fourth plus 1 if you want, it's not going to work, because I can make up an x squared at the top. I can make up a 4, I can make up a 2, or any number, but I cannot make up x to the third. And I don't have that. So then I said, okay, maybe if I denote y by x squared, and the differential of y is 2x dx, and then I say, okay, now I see where I'm going. This is okay. The only thing that I'm missing is a 2. And then 2x dx will be replaced by dy. And the denominator, which is 1 plus x to the fourth, will be replaced by 1 plus y squared. Of course, the 1/2 has to stay in front. And from this point on, it's clear, because I know that this must be arctangent plus a constant c. Of course, y. It's arctangent y. At this point, I have to replace y by x squared. So this is 1/2 arctangent x squared plus a constant c. Again, if you have any doubts, you should check it. You should differentiate this. Make sure that you get x over 1 plus x to the fourth. Any questions on the procedure? Any comments? Any comments, anyone? Okay, so let's look at a trig one now. Sine x over 1 plus cosine squared x dx. Okay, can anyone give it a shot? Any idea on how to what a substitution to use? Many times when we see sine or cosine, we should think of the substitution either sine or cosine. Many times. I'm not going to give a recipe, but many times. The problem is that if I consider this, I don't have dy in the problem. For this, I don't have, so sine prime is cosine x dx. I don't have this in the problem. But what I do have in the problem is dy, which is negative sine x dx. Nobody cares about a negative. I can make that up in my sleep. Can multiply twice by -1. That doesn't mean anything. It doesn't make any change. And now this is my dy, and this is 1 plus y squared. So everything is accounted for. So from here, go here, negative, the integral from dy over 1 plus y squared. Same thing, arctangent y plus a constant c, or minus arctangent, go back to y, which is cosine x, plus a constant c. Any questions? Any questions? Anyone? Is this okay? What about this? Integral from e to tangent x secant squared x dx. What do you think about this one? Any idea about a substitution?
Derivative of tangent secant squared.
So yes, so absolutely. And especially, I see another, in e to the x is a function. So yes, this is my target indeed. As long as dy is in the problem, or very close, because otherwise I cannot make up functions and x and y and stuff like that. And it is. Very nice. So this is my dy. So then the integral becomes e to y dy, which is cannot be simpler than this. E to y plus a constant c. So when I replace, I have to go back and replace y by tangent. So the answer is e to tangent x plus a constant c. Okay, here's another. The integral from x squared plus 1 from times x to the third plus 3x, everything to the fourth dx. You could say on this one, just raise it to the fourth power, distribute, and you're done. True. I could. It's cumbersome, but I could. But it's much easier if we use a substitution. You can use any letter. You don't have to use U or Y or T. Use any letter you want, but not X. You can use A if you want. It doesn't matter. Can anyone give us a substitution? Potential. This is not the mathematical way, but what bothers me is this. This is what bothers me because it's inside function x to the fourth. So this is where I start. I don't know. As long as dA is in the problem, 3x squared plus 3 dx. So if I factor out 3, I see I'm in business. I need a 3, no problem. That I can make up anytime. Multiplying and dividing by 3 doesn't mean anything. Doesn't change anything. This is the way I like to do it, but you don't have to. You can just solve for dx or solve for this. And you say, oh, so x squared plus 1 times dx, x squared plus 1 times dx is dA over 3. That's the same thing. It's up to you, whatever. It's easier for you to see. It doesn't matter. The result is the same anyway. So from here, we have 1/3 in front, one more time, 3, and x squared plus 1, and dx, 3, x squared plus 1, and dx, they're all inside dy. And this is very nice now. That's the only part that I didn't account for yet. It's a to the fourth power. I want to show different letters, but look what I go back to y. That's not what I meant. It's dA, of course. Okay, so then, nice and easy. 1/3 a to the 5th over 5 plus a constant c, or 1/15 x to the 3rd plus 3x to the 5th power plus a constant c. Any questions? Any questions? Should we go now to